Okay, get this. What if I told you that you could prove something like 2 plus 2 equals 4, not with a bunch of symbols, but by drawing a shape? Sounds kind of wild, right? Well, today we're going to dive into something called cubical type theory. It's this pretty revolutionary idea that literally turns abstract logic into geometry. So, here's how we're going to tackle this. First, we'll look at a really tricky problem that's been bugging mathematicians. Then, we'll check out the cubical solution they came up with. We'll see how this whole thing turns the idea of equality into a path. You'll see what I mean. And then we'll get to the big payoff and wrap up with why any of this should matter to you, even if you're not a professional mathematician.
All right, so let's jump right in with the problem. And honestly, it's a problem that gets to the very core of a question you might think is super simple. What does it really mean for two things to be the same?
I mean, you and I know that 2 plus 2 and 4 are the same thing, obviously. But to a computer, they just look different. One is an operation, the other is a number. So how do you write a program that can understand that two things, even if they're structured differently, are fundamentally identical? That, right there, is the core challenge. You see, for a long time, the kind of formal logic used in math and in computers had this massive blind spot. It really struggled to treat two objects as the same, even when they behaved in the exact same way. The analogy of the keys is perfect. Imagine you have two keys that are perfect copies. They both open the same lock, right? But a computer might just look at them and say, nope, different. Just because, I don't know, they were made on different days. It couldn't see past the surface. So to fix this brilliant mathematician, Vladimir Voevodsky, came up with a pretty radical idea. He called it the univalence axiom. And the gist of it is this. If two things are structurally equivalent, they're perfect copies in how they work, then we should just be able to treat them as being identical. Simple enough, right? But here's the catch. For years, this was just an axiom. And an axiom is basically a rule you have to accept on faith, without any proof. So how do you prove an axiom? Well, here's the thing. You don't. That's not how axioms work. Instead, you build a whole new system from the ground up. A system where it doesn't need to be an axiom anymore. And this is where things get really cool. Enter a brand new geometric language for math called cubical type theory.
Okay, so the big idea here is a massive shift away from just abstract symbols on a page to something you can actually picture. Instead of pure logic, this system is built on geometry. We're literally talking about points, lines, squares, and, yep, eventually we get to the cubes.
All right, let's build this up from scratch so you can see how it works. In this new world, I want you to imagine any mathematical concept you can think of. A number, a function, whatever, as just a single tiny point in space. And here's where it gets really clever. So how do you show that two of these points are the same? Well, you don't write an equal sign. No, you draw a line between them, a path. And that path is the proof of equality. Sameness becomes a literal physical connection. It's not just an idea anymore. But okay, what if there's more than one way to prove two things are equal? What if there are two different paths between your 2 points? Well, how do you prove that those paths are themselves equivalent? Simple. You just fill in the space between them and create a surface, a square, just like this. We are literally building shapes out of proofs. It's incredible. All right, so we've got this new toolkit. Points, lines, surfaces. It's cool, but what can we actually do with it? Let's look at a real example of how this works in practice. The real game changer here is that we can now construct proofs in this super direct, tangible way. We're not just relying on a bunch of abstract rules anymore. We can actually build geometric objects that are themselves the proof. Okay, so take a classic problem from computer science. Imagine you have two functions. We'll call them f and g. Now, every time you give them the same input, they spit out the exact same output. Intuitively, you'd say they're the same function, right? But proving that formally used to be surprisingly tricky. But with this new cubical method, we can actually do it. For every possible input, we can draw a little path between their identical outputs. And then, and this is the cool part, cubical type theory lets us weave all those millions of tiny little paths together into one giant higher dimensional path that proves once and for all that function f is identical to function g. The path itself becomes the proof. And all this incredible geometric machinery, all the points and the paths and the cubes, it was all built for one main reason. It was all leading up to this, to finally prove Voevodsky's univalence axiom. Remember that idea we talked about a minute ago? That sameness is equivalence? For so long, that was just an article of faith in this whole field of math. The Holy Grail, really, was to build a system where you could prove it step by step, right from the very foundations.
And just as a quick reminder, this whole axiom thing is a huge deal. Why? Because it finally aligns formal, rigid, computer-checked math with the way human mathematicians actually think. It's what lets us finally say, look, if it walks like a duck and quacks like a duck, then for all mathematical purposes, it is a duck.
And this right here is the big payoff. In all the older systems, like Homotopy type theory, univalence was just an axiom, a starting rule you had to assume was true. But in cubical type theory, because we can physically build our proofs with these paths and cubes, univalence stops being an assumption. It becomes a theorem, a statement that has been proven, without a doubt, from the system's most basic building blocks. I mean, this is a huge landmark moment in formal mathematics. By turning logic into geometry, this system took one of the most important foundational beliefs of the field and turned it from an article of faith into a demonstrable, rock-solid fact. So you might be thinking, okay, that's cool for theoretical mathematicians, but why should I care? What does this breakthrough actually mean for the rest of us?
Well, the implications are actually huge. It means we can build way smarter, more intuitive proof assistants. And that's just software that can double-check the correctness of, well, almost anything, from a super complex mathematical theorem to the critical code that runs a hospital's equipment or self-driving car. It makes formal computer proofs feel much more like the way humans actually think and work. The bottom line is, it's about building a more powerful and, frankly, more reliable foundation for both math and computer science.
When you step back, what this whole breakthrough really shows is the power of a new perspective. Just by turning an abstract idea like equality into a tangible thing, a path, we solved a problem that had stumped people for years. It just goes to show you that sometimes the biggest leaps forward don't come from finding a new answer, but from finding a completely new way to even ask the question. And that leaves you with a really fascinating thought. If equality is a path, what other profound ideas are out there just waiting for us to see them in the right shape?